Hi, folks. Today we're going to talk about a big question, and that is, what is mathematics? And it's a very big question in that there is no good answer. Well, that's not true. There are many good answers, but there is no unique answer. And so there are many good definitions of mathematics, but there is no actual formal definition of mathematics. If you ask 100 mathematicians, you're going to get 100 different answers. And this is kind of problematic when we're talking about a field which focuses on rigid definitions, if that's how you define it. I mean, numbers are clearly a part of it, but so are shapes and logic and maybe music or physics. What about physics? Is art math? I mean, what do we classify as math and what do we not classify as math? Where do we draw that line? What is it that makes math math? And that's what we're going to try and describe today. And so here's some guiding questions to help us understand this question. So the first one is mathematics invented or is it discovered? The second is, what kind of things are definitely mathematics? And then what kind of things can we label as not mathematics? And then what characteristics unite all of these ideas? This should help us develop some definition. I guess one big question, though, is what's your definition before we even begin? All right, first question, is mathematics discovered? And so for it to be discovered, that would mean that mathematics is already out there existing, and humans are just going out and discovering it all. And that kind of makes sense. I mean, there are mathematical structures which humans have discovered. There are many mathematically structured objects seen through biology and physics. We can talk about music being just a bunch of waves easily modeled by trigonometry and exponential functions. And so in this respect, the mathematics is already out there. We're just kind of exploring it. On the other hand, is math invented? For math to be invented, it would mean that math isn't something that already exists, but is something created by people. And this is also definitely the case. The universe doesn't have a quadratic formula written down anywhere. It's something that people wrote down. People had to think about this stuff. They thought it into existence. Sure, the universe satisfies formulas and whatnot, but people had to actually come up with ways to express these ideas. One common example is the idea of a triangle. There's no such thing as a triangle in the universe. There are shapes which are triangle-like, which have characteristics similar to triangles, but there's no actual triangle in the universe. It's all just a bunch of atoms which are vibrating really crazily. And so in that respect, mathematicians are developing the tools to understand this stuff, and the mathematics is invented. And so is it discovered or invented? It's a little bit of both. And we need to think about that when we're coming to decide how we're going to define mathematics. It describes the objects and structures. And so it's something which is discovered. But it also describes people-created tools, which we use to explore those objects in nature and whatnot. And so somehow we have to take into consideration both substance and structure when we're thinking about this. And so what kind of things are definitely mathematics? Well, there's the obvious, numbers and shapes, algebraic manipulation, geometry, logic, mathematical structures. These are all things which are definitely mathematics. There's also some less obvious ones. Music. I mean, we keep mentioning music. Is music math or not? What about art? What about language? What about economics? Are things which use a lot of math themselves mathematics? And, when we're thinking about defining mathematics, there's a lot of different things which use a lot of mathematics, which we might not define as mathematics. In the case of language, we can analyze the structure of words and syntax. We can consider grammar. We can investigate how words have evolved with time. and even look at the geometric structure of our letter symbols. These ways of analyzing language are mathematical. They definitely are. But does that put language itself in the mathematics category? Well, before we move on, let's think about things which are not mathematics. And this is more tricky because everything's got a little bit of math in it. But in talking with some colleagues, we came up with two big examples. The first is statistics. And so statistics uses a lot of mathematics. And so at its best, statistics is a tool which uses mathematics to understand data. At its worst, it's a tool which uses mathematics to support a narrative which may or may not actually be true. A common expression is there are three kinds of lies. There's lies, there's damned lies, and there's statistics. The important distinction here is that statistics uses mathematics to tell a story or support a claim. Mathematics is more about unraveling universal truths, and statistics can be easily manipulated to tell untruths. Another example which we came up with was science. And so the scientific method focuses on creating a hypothesis and seeing if we can disprove the hypothesis. With sufficient evidence, a good hypothesis can become a theory. That is not how math does things at all. In math, we focus on rigorous definitions and prove things to be universally true. Science focuses more on reality than mathematics. There are no actual triangles in the universe, just triangle-like objects. And so with science, it's more experimental, it's more observation-based. When we think about examples like patterns, sometimes patterns can be leading us in one direction, but the reality will be different once we get to a certain point. In mathematics, we want to figure out what's causing that. What is the underlying nature of things which are causing things to change? In science, it might take a while to actually uncover that that pattern isn't true. And so it's really structural differences. Science focuses more on the inferential side, whereas mathematics is more on the deductive side. Bringing these ideas together. And so mathematics is about structures. Structures we discover, structures we invent. There's an element of we involved in that mathematics is a thing which is done. Math can be used in other fields, but not everything is mathematics. And so mathematics is a tool set. There is a mathematical method to analyzing structures, similar to science and the scientific method. And there's also some element of truth related to mathematics. We prove things. Evidence alone is never enough. Proofs rely on clear definitions and conditional if-then statements to prove philosophical truths. We have to have clear, rigorous definitions in order to do this. When we think about numbers and what it means to be an odd or an even number, we have rigid definitions for what odd and even mean, so that when we see a number, we can classify it clearly as one or the other. That's one of the defining characteristics of mathematics. Another thing, in mathematics, there is an observer who is investigating structures to understand truths. With this, we can probably form a decent definition. And here is the definition I will put out into the world. Mathematics, a definition. Mathematics is the study of universal truths through the analysis of definitions and conditional statements. It is a subject which at its core focuses on an understanding of substance and structure and can be thought of as the study of absolute certainty. And so, substance and structure. When we think of substance and structure, it means that we see the forests and the trees, and then we seek to understand how they are connected to one another. And that's really a big part about mathematics. We can recognize different objects and then try and figure out all of the connections and all of the different structures which are involved in them. And so in mathematics, we appreciate the strumming of strings, but then develop a mathematical structure for notes and chords and further expand to melodies and songs. A lot of this was done 2,500 years ago by the Pythagoreans and even before then. In art, we can see a beautiful painting and then analyze its composition based on balance, emphasis, unity, movement, and a variety of other structures. It's a tool set for such analysis. And the study of mathematics is all about developing tools to better understand the world around us. It allows us to explore the structures of reality, and in doing so, gain a deeper understanding of the material. It's not enough to see the forest and the trees, but we have to understand the leaves and the birds which live within it. Again, thinking of the triangle example, it's about trying to understand triangles so that we can understand the triangle-shaped objects that are around us. But also, we just like triangles, and so we can just explore triangles for the sake of triangles as well. Exploring mathematics. And so the content of this series of lectures is going to explore 4 core units of material. The first is an introduction to mathematics, which is what we're currently focused on. What is mathematics? Where does it come from? What's a pattern? Just the very, very most fundamental aspects. Our next unit, our first math unit, is going to be the structure of sets and numbers. And so how do we explore collections and connections of numbers and other things? Really, this is all about the structure of structures. What is a set? And what different types of sets are there? And how can we explore the world from a set perspective? The next is the geometry of change. And so how do we connect shapes to movement and use it to describe a chaotic world? When we think about geometry, we have the old school geometry from the Egyptians and the Euclideans and the Greeks and all of them. But then we have how it changed in the last 1,000 years, where it transitioned to analytic geometry. And then there's even more specific geometry from the last 100 years or so, when we start talking about chaotic behavior and fractal geometry. And so we're going to focus on geometry through this idea of how geometry can change things. And then our last unit will be on truth and damned lies. That is where we are going to talk about certainty and uncertainty. What does it mean to be truth? What does it mean to be false? How can we understand statistics, and how can we learn how to lie a little bit better using statistics, or recognize when we're lied to? And so that's going to be the focus of this lecture series. We're then going to bring all this information together, try to understand the world around us. That is going to be a very large theme from this series. And so here is a brief listing of the type of structures which we are going to explore through this lecture series. We are going to have sets and numbers. We're going to have the geometry of change, and then our truth and damned lies. And let's explore all of these different topics one at a time. Make sure that we have some baseline introduction to them before we go in depth throughout our lectures. Our first topic is number theory. So number theory at its core is about the structure of numbers. So prime numbers, rational numbers, how do they interact with one another? A lot of discussion regarding the primes and composites, as well as divisibility principles. Many of the patterns and algorithms discovered throughout arithmetic fall into number theory, but there are many other patterns which are less commonly explored. We're going to go in depth into some of the fundamental ones. The next big topic is discrete math, and this is one of the large branches of mathematics. Discrete math is the broader form of number theory, which focuses on countable objects. This includes things like modular arithmetic, which is like the motions of a clock, doing computations in different number systems. It also includes most of computer science. Not all countable things are counted, and understanding the structure of these objects is important. Yeah, here's an example where we can think about how do you position desks in a classroom? That is a problem of discrete mathematics, and there are a lot of different approaches. Set theory. Set theory is one of the most foundational branches of mathematics. When we think about it, set theory is really the basis for most of the other mathematics which you are going to explore. And because of that, we had to make sure that it was very, very solid. We didn't want any paradoxes in set theory, and so it all got rewritten at the early 1900s so that it would be very sound. There are sets we use frequently, such as the set of natural numbers or real numbers, but there are also ways we can combine sets or define new sets in terms of other sets. Set theory gives us a language for exploring these collections of objects. Topology is a natural extension of set theory, in that it allows us to explore more abstract objects. Point set topology is really just the study of unions and intersections of sets. And when we think about that, that's just the study of Venn diagrams. It's all just taking set theory and then adding a little twist to it. More broadly, topology can give us a way to analyze algebraic and geometric structures such as knots, the torus, and Mobius strips. We can get into very abstract objects, and we can also get more down-to-earth objects too. In particular, Earth. When we think about the Earth, what is the shape of the Earth? Is it a sphere? Well, not quite, but close. And so how can we describe an object which is almost spherical, but not quite? Topology gives us the tool set in order to understand objects like that. The next big one is graph theory. Personally, I think graph theory is one of the most important structures for us to learn, and I wish it were introduced more thoroughly in K-12. Graph theory is where discrete math and topology meet. It gives us a way to organize information and see connections between ideas. And so a graph is simply a collection of points and connections. And we can apply numbers, information, directionality, or whatever we want to these points. These are one of the most important mathematical structures for understanding the world around us. When we want to understand how things are connected to one another, that's what graph theory is all about. Graph theory is all about trying to understand this idea of connection. The next topic is abstract algebra, sometimes called modern algebra, sometimes just called algebra. And so abstract algebra takes sets and introduces operations such as addition or multiplication. No, none of these others that we've talked about so far have really focused on the idea of adding. And so this is the first time where we're really introducing this idea of addition. And then it explores the properties which arise from things like this. And so the numbers on a clock under the operation of addition satisfy associative property and commutative property. What about under multiplication? And so if you take a 2 and you multiply it by a 7 on a clock, well, that would give you 14, which would put you back at 2 o'clock. And that's kind of interesting that 2 times 7 equals 2 when you're talking about that type of multiplication. This gives us a way to explore algebra on things which might not be nice number lines. And one common example is the rotations of a Rubik's Cube. The rotations of a Rubik's Cube satisfies a number of algebraic properties, and understanding those algebraic properties can help us manipulate it. The next big one is Euclidean geometry. Euclidean geometry has been taught using the same textbook for over 2,000 years. It is solid. It is very well defined, and really it designed how we approach other mathematical topics. It is known as the axiomatic approach to mathematics. And so when we think about Euclidean geometry, often we focus on geometry of the plane, but also constructions with compass and straight edge, a little bit of trigonometry, maybe a little bit of 3D geometry, particularly related to the Platonic solids. But then it raises the question of, if you have Euclidean geometry, what is non-Euclidean geometry? And we have to play around with the axioms a bit in order to understand how that can change. Essentially, when we think Euclidean geometry, we're thinking about it on a plane. Non-Euclidean geometry might be the geometry on the surface of a sphere. And so if you are going from the North Pole to the South Pole, there's a number of different paths you can take. If you need to intersect through a third point, or maybe 2 other points, the geometry starts to be a little bit different than if everything was flat. Analytic geometry is the next big one. And analytic geometry really spawned a lot of mathematics. Analytic geometry is what we usually think of as graphing. And so what is a function and how do we graph it? What types of graphs can we make? And when it comes to lines and curves, how can we use their slope to understand their structures? Analytic geometry was a milestone, and we have built so much math based on that idea, including calculus. Calculus is the study of how things move, grow, or otherwise change. When given a function, it's just the slope. Really, we could just say, instead of calling it calculus, we could just call it the slope. That's it. That's the entire calculus. There are many notations for it and many applications. After all, can you name a field where nothing moves, grows, or otherwise changes? There isn't one. If there is, you should get it out of that field and find something new. Differential equations is then a field which goes a step further and shows how we can model all things using these changes. If we want to figure out how populations of bunny rabbits and wolves interact with one another, we can do that using differential equations. If we want to figure out how pandemics occur, we can model that using differential equations. Next big topic is measure theory and metric spaces. These are ideas related to how do we measure things. And so measure theory is more about quantities that we're dealing with. And so when we think about eating a tub of ice cream, we can think of each spoonful representing a measurable set. And if we take all of the spoonfuls out of the tub of ice cream, well, we have measured the full container of ice cream. When we think about metrics and metric spaces, really that's more about how can we measure things, as far as there are many different approaches to measuring distance, for example. If we wanted to measure the distance from point A to point B, we could say, how long would it take if we are taking a car? Or what would be the path which we would take if we were to be a bird going through the sky? Or we could do even more abstract things. What if we were to tunnel through the earth? What would that distance be? And so metric spaces and measure theory gives different ways to approach this idea of measuring things. Ooh, next is chaos theory. So chaos theory is a broad area of mathematics which explores deterministic events. Chaotic behavior is when a small change in initial conditions can have substantial effect on the overall outcome. It's sometimes taught as the butterfly effect, the idea that a butterfly flapping its wings can cause a tornado on the other side of the world. And we can do math with that. So we're going to introduce a little bit of math related to that. Next, we're entering our last unit, which is all about truth and lies. And symbolic logic really gives us a grounding for it. So symbolic logic is a way of exploring when a statement is true or not using truth tables. How does an if-then statement really work? And what types of statements can we analyze? If A or B is less than 0 and A is not less than 0, can we logically say B is less than 0? How do we prove such a statement? These types of logic form the basis of all computer science, but really it forms the basis of all of mathematics. Set theory is based on this idea of symbolic logic, or logic in general. And when we are thinking about how we can describe all of the other mathematics topics, it all comes back to this original idea of logic. Our next big topic is combinatorics. Combinatorics is the study of counting principles. And while it's its own thing, usually we group it together with probability, which I'm guessing is our next topic. Combinatorics is all about counting things. So suppose that you have 5 different colors and 3 boxes to color. How many different ways can you color these 3 boxes? What if you can't repeat the same color twice? What if the middle color cannot be red or yellow? What if you can mix the colors? And so all of these different things lead to different ways that we can count things. And counting becomes important when we're talking about probability. Probability is closely tied to combinatorics. While combinatorics counts possible events, probability asks what is the likelihood of that particular event occurring. And so this is all about likelihoods. Suppose you have three colored balls, R, B, G, and so red, blue, and green, in a bag and pick two at random. What is the likelihood that the remaining ball is green? What if instead you picked a random ball, returned it to the bag, and then picked another random ball? What is the likelihood that you didn't select green either time? Will these two cases give different outcomes? Is the likelihood different for both of these? Well, those are the types of questions probability seeks to ask. There's then data analysis and statistics. Data analysis involves collecting, organizing, analyzing, and interpreting and presenting data. Statistics is often used to present information in a common way, such as summary statistics that describe shape, center, spread of a data set. But one thing to be very aware of is that both are dangerous. While math seeks the truth, statistics can be used to hide or distort the truth. And so, as mathematicians, it's important for us to understand the data and understand how statistics is used so that we can understand the actual truth of whatever situation is being presented. And that is a very big challenge. And it always goes back to looking at the data. Our final thoughts on the question of what is mathematics? Well, the most important thing to realize is that mathematics is all about understanding and analyzing structures. And there are a great many structures out there. The different branches of mathematics listed above are just the tip of the iceberg. Some are more relevant than others, and a thorough understanding of these structures will allow us to better understand the world around us. We've now seen broadly what all of these topics in math are. This lecture series is now going to go in depth into every single one of them. We are going to try and develop a baseline understanding of what these topics actually are about. We are not going to be going in depth into any of them, as far as this would not be the equivalent of taking each of these courses. For instance, we're going to introduce the topic of calculus, but we're going to introduce the topic of calculus from a perspective of you've only seen the basics of algebra before, and we're going to build up to those ideas and then try to understand it in broad pictures. We want you to have some general understanding of mathematics. That's the point of the survey of mathematics. With that, I'll let you get to work exploring where you can find mathematics in the real world. Good luck, folks.